One of the really cool things in science is how scientists have inferred the average density of the Earth. The average density of the Earth is actually a relatively well-known number. That's about 5,448 kilograms per meters cubed. Well, how in the world do scientists know that number to such high precision? Well, it's actually pretty clever. Remember that density is equal to mass divided by volume. Now, the Earth is very nearly spherical, so we could write this as then the volume of a sphere is 4/3 pi times the radius of the sphere cubed. So if we knew the radius of the Earth and we knew the mass of the Earth, we'd be able to calculate its density. And that's indeed how the density of the Earth was calculated. So let's talk about how scientists are actually, I don't know, they were just people back then, were able to first determine the radius of the Earth and then determine the mass of the Earth. Because if we know those two things, we can compute the average density of the Earth. The density, I'm sorry, take it back. The radius of the Earth was actually first determined and measured with an incredibly high degree of accuracy back in 200 BC by a guy named Eratosthenes. And Eratosthenes was a Greek scientist, a Greek naturalist, who made the following inference. He had already known that the Earth must be spherical. And if you imagine a part of the, I'm going to exaggerate the spherical surface of the Earth here now. So he had friends and in different cities in Greece, and there was one place where there was a deep well, vertical well, and at a certain time of day it was known that when the sun here was directly overhead, that would illuminate the bottom of the well. So the sunlight would only be able to illuminate the bottom of the well when it was directly overhead. At that identical time, his friend, some distance away, reported that a vertical staff on the ground cast a shadow so that it wasn't directly underneath the sun because of the curvature of the Earth. And that shadow, let me make that larger to make it a little easier to see. So here's the staff in a nearby city that's casting a shadow here on the ground. And he could measure this angle here, the angle that the sun made with that vertical staff, that staff that was perpendicular to the surface of the Earth at this location here. And then using a little geometry, these were people who knew geometry, right? If he knew that angle theta there, I'm going to run out of room here, so bear with me here. It's supposed to be a straight line, okay? That angle must be the same as this angle theta. And if he knew this distance, the distance between his observation and his friend up there with the vertical staff, then it should be a simple matter from geometry to calculate this distance, which is the radius of the Earth. And when he did that, he got a radius of about 6,400 kilometers, which is remarkably close to today's value of 6,350 kilometers. Remember, it varies a little bit because the Earth isn't perfectly spherical. So back in 200 BC, people had already figured out that the radius of the Earth was about 6,400 kilometers, and therefore they knew really well, we could calculate really well what the volume of the Earth had to be. So the next question, and if we wanted to actually calculate the density of the Earth, was to get at the mass of the Earth. And that was a much thornier problem that wasn't solved until much, much later. In fact, it wasn't solved until nearly 1800 to about 1798, when a scientist named Cavendish did a very clever experiment that was able to infer the mass of the Earth. So Cavendish in 1798 did a very clever experiment that allowed the mass of the Earth to be calculated. Well, remember from Newton's law of gravity, it's that the force between two objects is equal to this gravitational constant g times the mass of the product of the mass of the two objects divided by the distance between them squared. So this was well known from Newton's time. And furthermore, we know that on the surface, we know that Newton's law of acceleration says that the force produced by a body being accelerated in a gravitational, or being accelerated, um, is equal to the mass times the acceleration. And on the surface of the Earth, we call that acceleration due to gravity at the surface of the Earth, little g. So I'll call this m1. We have some body here on the surface of the Earth that's accelerated by the gravitational force, and we can write that force as m1 times g. So if we combine these together, we can see that the force, which is m1g, is equal to g times m1 m. Now here we have this m2 now is the mass of the Earth, divided by r squared, which is the distance between the surface and the center of the Earth, which we just said we know. And so if we know all these things, these are going to cancel. We can measure little g. And if we know big G, then if we could know this big G, this gravitational constant here, we would be able to look at an object on the surface of the Earth and measure the gravitational acceleration and back out of that the mass of the Earth. So it all boils down to designing an experiment that somehow will allow us to compute what this gravitational constant g is. And Cavendish's experiment was very, very clever. He had two metal heavy lead balls separated by a stick, and he had another set of lead balls separated by a stick. So these two lead balls should feel gravitational attraction towards each other, right? This one should be pulled to that one, and that one should be pulled in that direction, like that. And so I guess these guys were fixed, and these guys are fixed, and I'll draw a different color here. The ones on the blue stick here are attached to a vertical rod here, which can torque. And so as these balls here, the blue ones here, are drawn to the white ones, they will torque, right? They will create a torque around that vertical rod, which is very, very small, because the attraction between these two lead balls, as large as you could imagine making them, is still very, very small. The gravitational attraction between them is very small. Well, Cavendish's great insight, or great clever idea, was to attach a mirror to the vertical staff, and then using a light very, very far away, a light that went in here and reflected off the mirror, he was able to amplify that very, very small twisting of the rod due to the gravitational attraction between the white and blue balls, and measure the amount of deflection. And then knowing the spring constant, if you will, for the torque, he was able to actually measure the force, and he knew the masses of the two balls, and he knew how far apart they were, and from that he was able to actually, for the first time, measure the gravitational constant g. And once again, knowing this gravitational constant g, he was then able to measure the mass of the Earth using the equation right here. So Cavendish in 1798, for the first time using a clever experiment, was able to measure the mass of the Earth. The radius of the Earth had been well known, and when you put those two together, you ended up with a density, average density of the Earth, which is equal to its total mass divided by its total volume, which is very close to 5,448 kilograms per meter cubed. That's how the average density of the Earth was inferred.